Hello everyone, welcome to this new session on electromagnetic fields and transmission lines. Myself Dr. Soil Rana, and today we are discussing our topic which we discontinued in last session, which is capacitors. We are studying different type of capacitance types. The first one in the series we have seen a parallel plate capacitor, that is the most commonly used capacitor. Parallel plate capacitor we have seen, we have derived its expression. After that we have discussed a spherical capacitor, two spheres separated by some dielectric medium. Now today we will discuss about the coaxial cable. We will discuss coaxial cable capacitor. So this is also one type of capacitor. Whenever there are two different plates of charges separated by some dielectric, that is nothing but a capacitor. Now in this 3D diagram you can see we have a central conductor with radius A, and there is one outer conductor with radius B. It has some length L. As it is considered as line integral, we have to consider rho L, that is the line charge density. We know what is line charge density formula. It is equal to dq by dl. This is the formula for line charge. Now here we can see what is the example of coaxial cable. All of us, we have seen coaxial cable at our houses. So you might have observed with television set there is one antenna connected, and this television set is connected with some cable. This cable is nothing but coaxial cable. So there is some thick wire, a black wire usually, you can see there, and there is one inner conductor, the thick conductor. Outside there is one coating of plastic, and again outside that there is metallic net. Let us see that in some image. We can have some image here. We will try. We will see the coaxial cable. So coaxial cable, once we see the things, we can easily imagine them. So directly let us try to get some images. So let us see some example of coaxial cable. So here we can see various coaxial cables. Now this one is the one which we use at the house. This coaxial cable is normally used. There will be two conductors, one will be the outer shell and another one will be the, so here we can see the central conductor. Here central conductor is the first conductor, right, and then there is the covering for that conductor, and there is the second winding of conductor. and in between them there is a dielectric, that is the plastic. So here what we can see two conductors separated by a dielectric, that is nothing but a coaxial cable. Normally we connect it with the television. This is example of coaxial cable. The same coaxial cable capacitance we have to calculate. So let us go for the calculation. So here the same coaxial cable we are considering with rho L is equal to dq by dl. Now let us discuss some mathematical equation. Let us derive the coaxial cable expression. For that we will use the same method. We will take electric field intensity, we will calculate voltage, and then we will calculate the capacitance. So as coaxial cable is a line charge distribution, we have to refer the formula for line charge distribution. So if electric field intensity, if we consider electric field intensity of line charge distribution, we get E bar is equal to rho L by 2 pi epsilon r into AR cap. This one we have already derived in chapter 1, where rho L is line charge density. So now what is this rho L here? Already as we have discussed, this rho L is nothing but dq by dl, right? So this is first thing we take. Second thing common, we have to take the voltage and electric field intensity formula. Say we may have some radius b2 a, and we have some electric field intensity across the coaxial cable, that is V is equal to E bar dot dl bar. Now we have to consider the figure. In that we will apply the formula. So in place of E we will keep this one, and in place of dl we will consider the radius of the coaxial cable. So what we can write here? So V will be equal to integral of, this place we will write rho L divided by 2 pi epsilon naught, then epsilon naught AR cap, and this dr AR cap we have to keep. There we have dr dot AR cap. So these two dot products will become 1, right? So now for integration, what are the constant terms? We will take them outside. So here constant terms are this rho L 2 by epsilon naught is a constant term that we will take out. So what will be the remaining term inside? It will be, say, 1 upon, it will be dr, so 1 upon r. So we will integrate it and we will get the answer. Okay, so if we integrate it 1 upon r, we will get this electric field intensity as minus of rho L divided by 2 pi epsilon. So it will be log of r, where limits are b to a. So we will simplify it, we will put the limits. Log a minus log b, we will get rho L by 2 pi epsilon log of, say, b by a. Now this is the voltage. Now voltage and charge is related with capacitance. Capacitance is equal to q by v. So we can write Q upon this term rho L by 2 pi epsilon log of B by A. Further, if we simplify, we can put Q. What is Q here? Q is nothing but rho L into dl, that is differential length. For whole length we can put L. So what will be the modification here? It will be rho L divided by rho L by 2 pi epsilon log of B by 1. So this will be the solution. If we simplify, we will get the final answer, that is C is equal to 2 pi epsilon L divided by log of B by A. So this is the capacitance for a coaxial cable. So we have derived capacitance for parallel plate, for sphere, and now for the coaxial cable. Now let us discuss next topic, energy density. So energy density is like how much energy is concentrated. It is given by the work done is given by 1 upon 2 epsilon E square, and we also know that D is nothing but epsilon E. So here we can keep the D, so we will get omega is equal to, work done will be equal to 1 upon say D E. This is the relation between work done, D and E. Again, if we keep D is equal to epsilon E, so work done we can say 1 upon 2 E square epsilon. This is energy density. Now if we explore more, what is energy? This, if any field is there, there will be presence of all the vector, electric, and if it is moving current, then magnetic field is also available there. So these D, electric flux lines or electric field lines, they will be moving in different places in the space. So this relation of epsilon integral of E square into this particular dV is used to calculate the electric field intensity. So let us briefly see the Laplace 2 equation related to this chapter. Already in separate video in detail we have seen the Maxwell's 4 equation. So here we can revise them as, say, first one is which is related with this chapter is E bar dot dl bar is equal to 0. That means it's nothing but law of conservation of charges. Something starting at same point, closing at same point, the circular integral for this place will be equal to 0. Then we can apply some Stokes theorem for this. What is Stokes theorem? Stokes theorem states that we can actually, Stokes theorem is used to convert line integral into surface integral. For example, sometimes we get a question where one side of the expression will be a line and another side of expression, say RHS, may be surface. So this may be my LHS, this may be my RHS. For solving them, I need both of them similar. So what I will do for this line integral, it is a single integral. I will convert it to surface integral by using Stokes theorem. Stokes theorem uses cross product. Now what Stokes theorem says? It says that suppose if I have a line integral, here I have E bar dot dl bar. So this one I can convert to surface integral. How? I have to take the curl of my vector. In this case my vector is electric field intensity. So what I can do? I can do del cross E, that is the cross product. So once I take the curl of E, this will be shifted to ds. So now what I can say, it is EDL is equal to ds. So I applied Stokes theorem. Now if we consider a closed path where the total term is becoming 0, then what will be the curl? Curl for this expression will also be 0. Del cross E will be equal to 0. That means the circulation of electric field intensity, again the law of conservation, this will also become 0 in this case. So this is Stokes theorem. Then what we have to remember from this topic, we will discuss the important points what we have discussed. First thing, the negative sign in our expression indicates that electric field intensity is opposite to that of voltage. Electric field intensity is opposite to that of voltage, we have to remember. Then second point what we have to remember is voltage is a scalar quantity, right? And if we take del dot V, it is the gradient. Del is only one operator and it cannot be considered as a vector itself unless it is used with any other vector or scalar, right? So another form of Maxwell's equation is d bar dot ds bar. This is what surface integral is equal to rho v dot dv. Another takeout in our discussion in this chapter we have seen, that is del dot d is nothing but equal to rho v. This is also point form we have derived in this chapter. So Maxwell's equation, two expressions we can have in point form and integral form. So if we want to revise this chapter in short, so we'll derive it along with Maxwell's equation and the formulas of capacitances we have calculated. So first thing, in point form del cross E is considered as 0. Its integral form, say E bar dot dl bar is equal to 0. Then second point form, del dot d is equal to rho v, and another one is say d bar dot ds bar from Gauss law is nothing but equal to some volume integral where we take rho v dot dv. So these are Maxwell's equations, one in point form, another one in integral form. Now we have calculated capacitance formula. In general, capacitance is nothing but Q upon V. For parallel plate, C is equal to epsilon A divided by D. Third one we have seen, for spherical coordinate system, C is equal to 4 pi epsilon divided by 1 upon A minus 1 upon B. Then we also derived expression for coaxial cable. It is C is equal to 2 pi epsilon A divided by log of B by A. This is the summary of capacitance topic, which comes under the voltage, third chapter. It's all about, we started with current I, then we discussed current density, then we discussed electric field intensity, then we discussed voltage, and then we discussed capacitance. All of them are depending on each other. There are different forms for each other. So this is about this chapter. So let us see one example. Let us see examples in next session. Till then, have a good day. Thank you.